Okay, let us be back. So yes, so what we are doing here, we are decomposing the square matrix A matrix and an orthogonal matrix. A equals to Q into R. And our idea is this decomposition will help us to find all the eigenvalues of the matrix A. We will see how. Okay, fine. So of course, this is an iterative method. This is an iterative method. Iterative method means you have to apply the method again after each other, like again one after another, each step. Okay, and usually the future steps depends on the value of the past step. That's the idea of the iterative process. Same thing will happen here. Here the iterative rule, iterative method here is AK equals to QK into RK. Okay, at the kth step. At some kth step, I will tell you now. Okay, I'll tell you now that you decompose AK. At the kth step, you have AK QK into RK. Okay, right. But so, okay, I did a tiny mistake here. Just came off my mind. So A is decomposed into Q and R, where Q is orthogonal matrix and R is an upper triangular matrix. Okay, fine. Now this is the kth iteration at the kth step. AK equals to QK into RK. Okay, then what is the next step? What is the next? What should be the next step? AK plus 1. This is where you cannot predict. You might predict it to be QK plus 1 into RK plus 1, but no. That's where the method is coming into existence. It will be the swap of the two multiplications. That is, it is RK into Q. Okay. So AK, the matrix A at the kth step is given by QK, the orthogonal matrix at the kth step multiplied by the upper triangular matrix at the kth step. Fine. But the next step, that is the K plus 1th step, AK plus 1 is given by the swap of that. That is, first multiply the upper triangular matrix, then multiply the orthogonal matrix. Okay. You can see the difference between the two. Now, why, if we do this, what is the advantage? There is a very nice concept involved in doing this. Very nice concept involved. I want you to see it. Only these two statements will make you realize that. Are you able to realize by looking into these two statements? Can you tell me? Okay, okay. Fine. Let us write AK plus 1 is RK times QK. Fine. Now, is it correct if I write the next statement? Is it correct if I write this statement? Why? I did not do anything new. What I did is I multiplied the QK inverse and QK. Okay. So I just multiplied QK inverse and QK. And those two multiply to identity. So multiplying identity to a matrix doesn't change anything, right? Is it okay with you? Because if you see this whole thing, it might be fear. Just to see the first multiplication here. This is what I multiplied to RK. Everyone is okay with this. Now can you see something? Just in the previous class I told you about. Are you seeing something? What are you seeing? Q inverse, this QK RK, I can write AK. This QK RK is the same. Sorry, it's the same as the K step, isn't it? Happy with this statement? How many of you are fearing it? How many of you are not understanding? Anyone not? You did not understand. Okay. So what we are doing is, this is the first step we define. This is the definition. Okay. We define the K step to be AK. Okay. The matrix A is changing. the matrix A is changing throughout the iterative process. So therefore, the first iterative process, second step, it will be A2, third step A3, so on, it will be AK. Okay. So therefore, AK is written here. Now that AK matrix is decomposed as a product of two matrices, a product of K, an orthogonal matrix, and a product of upper triangular matrix. Okay. Why it is the case? That is not of interest. Okay, that's what researchers have found after a lot of investigation. Okay, so it is bear in mind that it is true that any matrix, any square matrix, mind my words, any square matrix can be decomposed into a product of orthogonal matrix and an upper triangular matrix. Yes. That is the statement. That is the statement, nothing else. Why it is the case, you don't have to worry about it. Okay. Just know that it is the case. Okay. Now, the next step, that is the future step, AK plus 1, how I am defining, that is where the essence of the QR method lies. This is the second step of the method. And this also I am defining that AK plus 1 should follow RK into QK. This is the rule. This is the iterative rule. Iterative process for QR. Okay. Fine. Now, I am telling you, I am giving you a motivation why we do it. Because it is easier to visualize it. Write down AK plus 1. It is RK into QK, right? Fine. Then what I do, I multiply in the front Q inverse into Q. That will be just identity, right? That will be just identity. So it doesn't change the matrix. Fine. Everyone understood till this point? Okay. So now what I am doing is, this is multiplied with each other. Now QK into RK, this should ring a bell in your ears that QK into RK, I have seen it somewhere. Where I have seen it? I have seen it in step 1. AK is QK into RK. So I just substitute it here. Yes, so QK inverse AK into QK, right? So you can see that AK plus 1 is written as QK inverse AK into QK. Now, one very nice thing is upper triangular matrices are invertible. Upper triangular matrices are invertible. Yes. What do you think? Yes. You can check it. You can check it. Upper triangular matrices are invertible. And you can see that this is an invertible matrix. This is an like P inverse AP. So what can you conclude? What can you conclude from this? What can you conclude from this? Like, it is just looking like B equals to P inverse AP. Then we say A and B are similar. So here what you will tell? Yes, this implies that AK plus 1 and AK are similar. What does it mean to be similar? That means the eigenvalues of AK plus 1 and the set of eigenvalues of AK are the same. That is the property that we discussed last class. Yes. So set of eigenvalues of AK plus 1 and AK are same from this property. Isn't it? Yes. So they will have all of the same eigenvalues. Now, as you keep on iterating, that's the job of your iteration, like iterative methods. You keep on iterating, that find AK plus 1, AK plus 2, AK plus 3, so on. Do the iterative process. Then you will see that as the iteration continues, you will eventually matrix converges, AK converges to an upper triangular matrix. Fine. You understood the statement of this? I'm not saying that I'm not saying the proof of anything. I'm just saying the statements. Proof will be very long and hard to follow. Proof is not the part of this course. Okay, just knowing the techniques and the application is the part. So therefore, I am telling you, okay, you can prove it if you like. You can see books in library. There are very nice books. So I suggest there are 2 books. I think one book I already shared on our Google Classroom. Right? Are you reading that book? See, the lectures I am giving to you are just like the eye drops. Okay, but you have to regularly wash your eyes, take good diet to make your eyes healthy. Yes, how to take that good diets and all. The book is a good diet for you for this course. Okay, so I strongly suggest that after I teach all this, suddenly like quickly go through the material of the book, practice through the examples. Gauss-Seidel method, please go through the book. I already mentioned in the notification. Anyway, so what I'm saying, this is the most important line of the QR method. This is the most important line. Okay, what is the most important line? You do the iterative steps of the QR method, and it guarantees that the matrix AK, which is of your interest, will converge to an upper triangular matrix. Okay, that is the statement. How it will look like? How it looks like upper triangular matrix? Can you tell me? So you can see that AK will, which is like RK into QK for you, it will be an upper triangular matrix. So can you give me how it looks? Okay, I'll write it. Maybe it has n number of steps, and these will be some numbers like I'm not writing it, so on. But others will be 0. Yes. Can you see like this? Is this an upper triangular matrix? Yes, because upper triangular elements are non-zero and lower triangular elements are 0. So this is an upper triangular matrix. But most importantly, it will converge to an upper triangular matrix. Fine. But this is your answer. Because the diagonal elements of that upper triangular matrix will be your eigenvalues. And this is what you need, right? This is what you needed. That is our aim, right? Power method gave you the dominant eigenvalue, but power method did not give you the remaining set of eigenvalues. Now, how to find the remaining set of eigenvalues? We jumped to QR method. Okay. And using the QR method, you can see that if you keep on iterating the process, it is converging to an upper triangular matrix, and the diagonal elements of those upper triangular matrix give you the eigenvalues. So you have all the remaining set of eigenvalues of the matrix A right here. Hope this is clear. Is this clear? Is this clear? So you can actually decompose the matrix at each step. Remind yourself that at each step, you have to decompose the matrix into an orthogonal matrix and an upper triangular matrix, right? And that is not an easy task. That is not an easy task. Okay. Given, I will give you a matrix A, and I will ask you that can you decompose into Q and R? It will be very tough. It will be very tough. You don't know how to start. Okay. So that is usually done. That sort of decomposition is usually done by something known as a, just need to know it, something known as householder transformations, but we will not cover it here. But you need to know how this kind of magic happens. Okay. This is not, we will not go into details of this, but know that transforming A into Q and R And the method of how to get this Q and R is usually done by this Householder transformation. Okay, fine. So we'll see using Python, like the QR method into action. Okay, I'll give you an animation in Python showing that actually you can appreciate that actually it is converging to the QR method. What I will do, I'll tell you before running it. Yes, you have from the package lin alg, you can import the QR method, okay, in Python. And the idea is like QR and the matrix. QR and the matrix. If you do that, it will automatically decompose the matrix A, square matrix A, into Q and R. It will give you, for a given matrix A, it will give you what is Q and R. What is Q and R? Okay, so that's the basic idea of this method. And most importantly, what I will show you in animation is, we will consider a matrix. Fine, a matrix A, and the matrix A is a set of numbers. The matrix A is a set of numbers. Okay, so what I was telling, I was in the middle of something. So I told you that we'll see some Python codes after this for QR method. You will see QR method in action. And then one more animation I will give, but before that I want to, you have a matrix as a set of numbers, 3, 4, 8, 2. Okay, so this is 3, 4, 3, 4 for square matrix, right? This is square matrix. Now I have another way of visualizing this square matrix. In Python animation of the QR method, what I will do is, I will treat this as a heat map. I will treat this as a heat map as a sense that each of these numbers will have a legend. It will be a color coded map. So maybe 0 to 10 and red to blue. It will be scaled. The colors will be scaled from red to blue. Okay. And in such a way that, so you can you now think that you can assign this 9 will look very bluish, isn't it? Color code according to this scale, 9 will look a bit bluish. 0 will look like reddish. Yes. 5 will look somewhat 50% blue and 50% red. Yes. So this matrix as a heat map, in terms of a heat map or a color coded map, will look like a colored square, isn't it? Colored square made up of different colors. Yes. Now we will run the QR method again to this matrix, and we will play with colors instead of numbers. Okay, we'll play with colors, and you will soon see that, of course, when you do the QR method, the values of the matrix changes. Values of the matrix A will change, right? That is what AK means. Yes. So if the values of the matrix, the elements of the matrix changes, what does it mean? The color will change. The color associated to these values will change. Yes. So you will see in the animation that the matrix is like a video, you will see the animation that the colors are changing. And after certain iteration, and somewhat here, okay, somewhat here, like an upper triangle. Finally, it is converging to upper triangular matrix, right? So you will see the colors only in the upper triangular part. In the lower triangular part, you won't see anything. So this is a graphical way of making you understand the meaning of QR method. QR method in action. So this is just, I'm telling you, this is a type of an activity of learning things. Like you learned one concept, then how well can you make it understandable to the wide audience? So this is one thing. So try to think of these concepts, or whatever concepts you learn, try to visualize along these lines. Okay? Visualize along these lines. So you can see that QR method was all looking matrices, no numbers, only symbols. Suddenly, we could come across colors. We are playing with colors. So therefore, whatever difficult the concept is, try to think of a way which can make it more intuitive to understand. Okay, let us be back to the code. I think this one. Yes. So this is the QR method you can see here. What I'm doing here, so you can see, as I told you, import numpy is NP as usual. Then from linear algebra package, LINALG package, I am importing QR. Okay. So that's where you import QR. Otherwise, it will not recognize what is QR. Okay. Then you define the matrix A. I should have written capital A. 0, 3. 0, 2, 2, 3. It's an invertible matrix, right? Yes, it's an invertible matrix. So how I do the QR factorization? Just write QR and then bracket the matrix A. Yes, then the matrix A. Then you have this Q and R. Now I'm printing this both Q, that is the orthogonal matrix, and R, that is the yes, R is the upper triangular matrix. Okay. Let us see what is happening. So as when you do this QR and A, Python quickly gives you the decomposition, that is the orthogonal matrix and upper triangular matrix. Check yourself. Can you see that this Q is in fact an orthogonal matrix? Can you see that it is an orthogonal matrix? For orthogonal matrix, what you need to do? Take the dot product of any two rows. Dot product of first row with the second row, it is coming 0, right? Take the dot product of first column and the second column. It is coming 0, right? Yes. So it's an orthogonal matrix. Done. So this is an orthogonal matrix and this is an upper triangular matrix. Is it an upper triangle? The low triangular element is 0. Fine. And is it the correct decomposition? Suppose Python is giving you, but you cannot blindly, you can blindly trust Python, but from humanitarian point of view, you cannot trust blindly. So how you can check whether it is correct? Again, you have Q and R, again multiply them back together. You should get back A. You should get back the matrix A. And that's what we have done here. When you multiply these two Q and R, you again generate the matrix A, which you have defined already here. Fine with you? Okay with you so far? Now the idea is, now the next example which I have done here is I have taken the same matrix, but here I'm not doing QR. Am I doing QR method in this example? Am I doing this QR method in this example? I have a matrix A. I just decomposed matrix A into Q and right. This is not the QR method. I just decomposed the matrix A into Q and R. The QR method is coming. Yes. So the next example will apply QR method to the same example, and we will do some 20 iteration for this. Okay. Of course, you can do as much iteration as you want. But here again, this is where we have this example. Yes. Okay. I am showing this matrix A, the same matrix A. Can you see it? See this example here. Don't worry about this array P. I will tell you what it is. Okay. Now I'm using a for loop. Like this is where the iterative process for the QR method starts. For I in range 20, that is I is going from 1 to 20, 1, 2, 3, 4 up to 20. QR, you apply QR is QR into A. Okay. That means A is decomposed into Q and R. Fine. What is the next step I told you? The next value of A will be the swap. RK into QK, right? RK into QK. R into Q. not Q into R, R into Q. So that's what is NP dot R comma Q. That's where R dot Q is done. Okay with you? Fine. What I'm doing with this P, not of many of you would have gotten this idea what is P, but what I'm doing is instead of plotting or instead of printing all the iterative matrix AK, A1 to A20 I have to print, right? Instead of printing A1 to A20, I am printing selected ones. I am printing A1, I am printing A5th, that is the 5th iteration, then I am printing A10, then I am printing A20. Okay. It is a very lazy way of monitoring things. Okay, what you do, how you watch whether, suppose I'll give you an example. One faculty has given, like, you were very mischief in class. Suppose Mr. Jubin was very mischief in class, and suddenly he did a very large mischief, not a small mischief, very large mischief. And due to that, now is not the case, but previously, like maybe 6 years before, maybe during my time, if we do some mischief, then finish. Okay, it is like grade back or 1 grade less or something like that. Okay, so that is a very heavy punishment. So one faculty does that to Jubin. Okay, then Jubin gets very demotivated, and then what will happen is he will, after the class, he wants to meet the faculty. Okay, so he'll go to the faculty cabin, like the office of the faculty member, but the faculty is not there. What will happen? And he is tensed. He wants to meet the faculty as much as possible soon. What he will do? At 9 he will go. Okay, 9, the university starts at 9, so 9 he will go and see whether the sir is there. No, sir is not there. Then 9:05 he will check. 9:10, 9:20, 9:30. So sampling, he will, at sample intervals he will check. Okay, or yeah, therefore that's a lazy way of doing the thing. So here also I am not, instead of printing all the matrices from 1 to 20, I am printing the matrices at some intervals. A1 at the 5th iteration, at the 10th iteration, how things are going. And I'm printing it. So here you can see it. What can you observe from this? Can you tell me? Observe the numbers here. Observe the data points here and tell me what you observe. Iteration 1, the value of the matrix A is as you have given. Sorry. No, the iteration 1, you did R into Q. So you have 3220. Then iteration 5, you can see that elements have changed considerably. Iteration 10, you can see, what can you see in iteration 10? Can you observe something from iteration 10? Iteration 10, you can observe that this guy is very tiny, isn't it? Iteration 20, this is even more tiny, 10 to the minus 12 range. So how about this? This is very close to 0, isn't it? 10 to the minus 12, almost close to 0. Then what about this matrix? This matrix is like an upper triangular matrix, which is as predicted by you. And what are the eigenvalues? Eigenvalues are these two entries, 4 and minus 1. That is the statement of the QR method. The QR method says that as you iterate your QR step, it will converge to an upper triangular matrix, and the diagonal elements of that upper triangular matrix are the eigenvalues. So this is the upper triangular matrix, and the diagonal elements, that is the 4 and minus 1, are the eigenvalues of the matrix. Okay. The final matrix and orthogonal matrix. Yes, it is an upper triangular matrix. It will be an upper triangular matrix. An upper triangular matrix can be an orthogonal matrix. Special case. Here it is a special case, I feel. Here it is a special case. But it won't be an orthogonal matrix if this guy was not 0, right? This guy was this guy getting 0. This guy is giving you the same value as almost same as this. So therefore you can see that this is a what do you call? So you can see that this is in fact a diagonal matrix. Why? Because only on diagonal elements you have non-zero quantity. Apart from the diagonal, you have zeros. But yeah, this is a good question. Can diagonal matrix be orthogonal matrix? Next class you will tell. Can diagonal matrix be orthogonal? Yeah, like this. So linear algebra is like this. Like you actually have to do. You actually have to visualize things. Most importantly, I will tell you that linear algebra is not something like it is being taught and you learn. You have to ask, you have to observe things, and you have to observe and connect things you learned in past. Like that, you will progress. Even in ML, you will be seeing a lot of linear algebra stuff, and you have to make converging to an upper triangular matrix. Is this a diagonal matrix? If this is a diagonal matrix, diagonal entry will be the eigenvalues. Like this, you have to connect to whatever you have learned. I am giving you a lot of weapons. You have to know when to use. That is the basic idea. Okay, fine. So now comes the most interesting part. Yeah, this is where I am doing it. Okay, I will not tell you. I will not explain this. Uh, I won't explain this detail. It's almost the same things, but I have converted the matrix into a heat map, which I just told before in the course. I converted the matrix into a heat map. So instead of a matrix with numbers, you will see a square with colors. That is the heat map. And I will run the QR method again and again, and I will show you an animation how the numbers change according to the colors. And I'll make you understand or convince you that actually during the QR method, things are converging to an upper triangular matrix. Okay. That means the lower entries will be maybe white color or no change at all. And only change will be occurring at the upper triangle. So this is what I have generated till 50 iterations. Don't mind this. Don't look at this. Directly to our main thing. This is a what happened here. Maybe I can see. Wait here. No. Okay. Anyway, so you can see that initially what had happened? Initially, this is the matrix A. This is the matrix A, which are scaled according to these values. So can you see what was the value here in this matrix? This is red. It should be around 1, close to 1. Then what is this one? Almost close to -1. Almost close to -1, blue. Okay. And this is the matrix. This is the iteration 1 of your QR method. Okay. Now I'll apply the QR method again and again to the. And of course, as you saw, the matrix elements will change. The value will change, right? Entries. We will see how the color changes. The color change is equivalent to saying the number change. And you will see something important. Yes, so suddenly it happened. It is going very fast. You can adjust the time. Maybe 1 second or 0.5 second I have set this. But you can see that it has converged to a diagonal matrix. Okay, because you are seeing only the colors in the diagonal. And you can even see what are the eigenvalues just from the colors. You can see one of the eigenvalue is 1. Yes, and one of the eigenvalue is close to negative. Okay, so yeah, this again started. So this is what using some visualization, I'm trying to make you understand intuitively the QR method. So I will share this with you in the collab. Of course, after you get these eigenvalues, you can compute eigenvectors. Okay. And that's what we are doing next. Of course, you have the QR method gave you, but QR method did not give you eigenvectors. Did QR method give you eigenvectors? No. But you have eigenvalues. From eigenvalues, you can compute eigenvectors. But in Python, you can use eig function to get that. So you can actually use this one, eig A, that is giving you both eigenvalue and eigenvector. Okay. Try to know through Googling or anywhere, any other source, that Python is using this eig function. Then what is happening inside this eig function? Magically, it cannot compute eigenvectors, eigenvalues, and eigenvectors. And numerically, we method to compute eigenvalues. My hunch is in Python. Python using inside, like in his inside algorithms QR method. See what is happening inside this eig function and let me know next class. Okay. Let me know next class. Or maybe let me know after the lunch break. Just one Googling will do this. Okay. What is happening inside this eig function? And as you see, both eigenvalue and eigenvector it is giving. Fine. Okay. So this is what QR method is. So if in exam we are asking you about QR method to do some QR method analysis, then we will be giving you A and we will be giving you the matrix Q and R. Okay, you don't have to worry about the orthogonal matrix Q and the upper triangular matrix R. It will be given to you. And it will be asked maybe do 3 iteration or 2 iterations of the QR method. Yeah, these are some of the applications. I just collected them. Yeah. So something like these are useful in your least square problems. Okay. So you will see QR method in action, and also it will help you if you do values through QR method. Your solution will be stable. Okay, it won't run unstable. I gave you an idea of stability and instability during linear equations. I just gave you a tiny change 3 to 3.01, and you suddenly saw that hugely the solution were changing. Those were known as ill-conditioned systems. Yes. So those are the systems. If you take, it will give you unstable results. And so yeah. So in machine learning, datasets often have a high dimensionality, and yes. So during feature selection and rank deficiency problems, it can be useful. Yes. So yeah, it can be also useful in PCA, that is principal component analysis. So keyword decomposition can be applied in the context of PCA. Okay. So let me know if you like if someone is teaching you PCA, maybe you can ask them how keyword method is useful in that. Okay. It will be a good idea there. Or it is already covered. Already covered. Already covered. But for data analytics, is it covered? Not yet. But you can approach it. You can approach it. You will see that both SVD, both singular value decomposition, and keyword method are very closely related to PCA. Okay, SVD, singular value decomposition, will help you in reducing the dimensionality. PCA will also help you do that. Okay. LDA. Yes, yes. I purposefully deleted this writing here, but I think it will come here. Yes, here. Eigenvalue problems. QR decomposition can be part of algorithm for solving eigenvalue problems such as spectral clustering, dimensionality reduction techniques, and LDA. That I reduced because it was crossing out of the text. Okay. But anyway, it is also being helpful in your signal processing in denoising stuff. If you give the signal, then QR method will help you denoise the signal. You intuitively think the heat map I gave you right now, the animation. You can think the noise present in the upper diagonal and lower diagonal elements, and you apply the QR method. And what QR method does, it eliminates the diagonal below the diagonal entries, right? And gives you the upper triangular element only. So what you can do, if you want to denoise your matrix, you can keep the diagonal entries just below the diagonal, keep the noisy terms and apply QR method. QR method will remove all those noisy terms. So that's where you can see that it is filtering and denoising in signal processing. Okay. So this whole things is a game of matrices. All the applications you see, even in biology, gene classification. Finally, what biologists do, biologists will do the gene analysis. They will classify, they will make a matrix, gene matrix. What the gene matrix will do, this person has this number of genes. Mr. Jubin has this number of genes. Then Mr. Aman has this number of genes. Mr. Aditya has this. Miss Durga has this number of genes. Okay. Then what will happen? There is you collect and store them in a matrix. You store all these genes in a matrix. Okay. Then see carefully, understand carefully that this is just a tiny example I have given. But if you are a biologist and some outbreak is there and you are analyzing the genes of a state or India, maybe India, billion of people. So the matrix will be of size billion cross billion. Okay. So how you will analyze? Of course, you have to reduce the dimensionality. Of course, there will be some noise in your data, in that matrix. There you can apply the QR method. Okay. To denoise first. After you denoise, you get a good matrix. To that good matrix, you can apply SVD that we will learn in our next class. SVD, when you apply the SVD, it will give you the best genes. When you store the genes in a matrix, what is your aim? To identify the best genes. Okay. And SVD, when you apply to that matrix, the clean matrix, will give you the best genes. This is a true application of SVD in biology. Okay. Anyway, so these are some of the applications. Just before stopping here, we have some time. Okay. Just before stopping here, we will look into some other transformations and just begin SVD a bit. And after lunch, we will full-fledged start with SVD. Okay. So, yes. Okay. No, I came way far. No. Let us see this. Let us see this penguin. You don't like penguins. Expression suddenly changed after seeing this penguin. Penguins are harmless creatures. Okay, so can you just look into this image and let me know? Of course, it has been stretched on the horizontal axis. So this is this image. This is just a penguin image, but actually visualize this image as a matrix of pixels. And what you do, you stretch it on both sides, and it became more fat. Okay, the penguin got more fat. Fine. What happened to this? What you do here? You rotated this clockwise. You rotated this clockwise, maybe 90 degrees. 90 degrees, and this penguin landed here. Then you rotated again clockwise 90 degrees, and this penguin lie here. Okay, fine. So this is the rotation. So I am giving you an example where your pixels are getting rotated. Okay, so this is, so whatever you are seeing, these two examples are like matrix transformations. Okay, you are doing some transformation to matrices. You are stretching the matrix and you are rotating the elements of the matrix. Anyway, so this is what I plan to cover this today. Okay. During the initial days of our class, I told you one. Yes, I told you one very nice fact. Walk and come. Yes, I told you one very nice fact. If A is a matrix, if A is a matrix, A is a matrix, okay? What you do, if you multiply a vector V1 to A, what will happen? Huh? Who told somewhere someone told here? Yes, you told, right? So you get another vector V2. So when you multiply a vector to a matrix, you get another vector. That's the very nice and heavy property which no one tells in linear algebra usually. Okay. This is the key fact of many heavy things you will learn. Okay. When you multiply a vector to a matrix, you will get another vector. Okay. But like this, can you predict where V2 will be? Where V2 will be? It is a vector, of course. That means it will have a magnitude and direction. But where it will be? Do you totally where V2 will be? Where V2 will totally depends on the entries of matrix A, isn't it? How the matrix looks like. If it is an identity matrix, suppose it is an identity matrix, then V1 and V2 are the same. V1 and V2 are the same. If it is A is this matrix, what V2 will look like? How V2 will look like? It is twice stretched. It is twice as length as the V2, sorry, as the V1, right? Because every element will be multiplied by 2. Every element of the vector is multiplied by 2, isn't it? Okay, fine. So this is what I am trying to tell you in this example over here. This we will learn what happens to shapes, what happens to different points. So if I take a point, suppose this is the xy coordinate, and this is one vector v1, and you have a matrix A. Okay. Now how AV1 will look like? AV1 will look like. There are two cases depending on matrix A. If A is diagonal, if A is a diagonal matrix, then stretching occurs. Stretching occurs. Okay. Stretching occurs. If A is an orthogonal matrix, then rotation occurs. So depending on the application, you can choose which matrix to multiply with the vector. If the vector is direction and you want the vector to be rotated by 30 degrees, then of course V2 is some orthogonal matrix O times V1. Okay. That orthogonal matrix will help you rotate that vector V1 by 30 degrees. Okay. If you want to stretch, then use diagonal matrix. Okay. You'll see that in this course. Now coming to this, let's do this example quickly. Suppose you have this matrix A equals to 3045. 3045, this matrix, and on both of the sides, you have the two x's over here. Now I'm asking what happens to a certain number of points. 0, 1. Can you tell me where 0, 1 is? It should be somewhere here, right? What happens to 1, 0? 1, 0 will be somewhere here, I think.